Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem ID 2872. Maximum number of K-divisible components. This is a tree-based question and has been asked in Google recently. And here in this question we will be utilizing concept of depth first search. Firstly, let's have a look on the problem statement. They are saying there is an undirected tree of n nodes labeled from 0 to n-1. So we have a tree where nodes are having label from 0 to n-1. Okay. And what is given to us? Given an integer n. Integer n is given to us and a 2D integer array edges is also given of length n-1. Why n-1? Because every tree of n nodes are having n-1 edges. Okay. Where edges I is equal to ai, bi, u and v. From source to destination there is an undirected edge. Indicate that there is an edge between nodes A1, AI and BI in the tree. Okay. You are also given 0 index integer array values. And what is values array? Values array is having value associated with the ith node. So values 0 is having actual value of 0th node. We were having nodes from 0 to n-1. Those were just labels. The values are in the values array. And apart from that, an integer k. And now what we have to do is a valid split of the tree is obtained by removing any set of edges, possibly empty, from the tree such that the resulting components all have values that are divisible by k. Okay, what he is trying to say is that from this tree, we have to split this tree in such a way using edges. Just remove couple of edges from this tree such that all the remaining subtrees, okay, they are having sum of values divisible by k. This is what they are saying, and what we have to return is maximum number of components in a valid split. So we have to make the component maximized. Split as much as you can. Just make sure that after every split, the component you are forming are having sum of all the values divisible by k. Okay, so let me help you explain this statement using an example. Here we will be given 4 items. First one is edge. First one is n. N is number of nodes in the tree. And number of nodes you can say from 0 to n-1. 0, 1, 2, 3, 4. These are the nodes in this tree. 0, 1, 2, 3, 4. You can say this is the label. And note the values. Values are in this array. So this values array are the values associated with the ith node. In this way, 0, 1, 2, 3, 4. And these values you can say these are the indices of this value. Okay. And apart from that, there is an edges array as well. Edges array is nothing. From index I to index j, there is an undirected edge. First one is 0 to 2. Where is 0 and 2? 0 and 2 are here. So this edge is there. 1, 2 and so on. Okay. First one is number of nodes. Second one is number of edges, which are n-1. And third one is values. Values associated with the ith node. And what is k? They are saying that the tree, if we sum all the values of the tree, it is divisible by 6. And we have to split this tree in such a way that from all the split values, the sum of all the split subtrees will divisible by 6. Let's see whether it is working on this example or not. Let's say for this subtree, what are the values? Nodes are 1 and 3. Okay. And at node 1 and node 3, what are the values? 8 plus 4, which is 12. Is 12 divisible by 3? Yes. Remainder is 0. And we can say yes, it is divisible by 3. And if I take off this, we have nodes 2, 4 and 0. 2, 4 and 0. 4 plus 1 plus 1, which is 6. 6 is also divisible by not 3. Given is 6. Okay, given is 6, not 3. So k value is 6. So 12 is divisible by 6 and 6 is also divisible by 6. Remainder is 0. Okay, so these are the valid split. If you have a look on the constraints, you will find out that they are saying that sum of values is divisible by k. It means that initially the tree is divisible by k. That is for sure. So there might be some possibility that if we divide the tree into subtrees, those subtrees are also divisible by k. Okay, there might be some possibility, or there might be the case where we are not able to divide it. Okay, and what about the other constraints? N value is going till this, edges dot length is n minus 1. Yeah, because it is a tree is always having n minus 1 edges, and n is the number of nodes in the tree, and all the indices are valid. Yeah, rest of the things are not important. Yeah, here you also have a look that values are 10 to the power 9 and the number of nodes are around 3 into 10 to the power 4. So if we keep on adding those into the integer variable, that might overflow. We'll see how to handle that. The input is generated in such a way edges represent a valid tree. Okay, the tree is always valid. Now the problem statement is clear to you that you are given number of edges and the edges from source to destination, undirected edges, and these are the values of ith node, and this is k. Ultimately the sum of all the nodes in the given tree is divisible by k, and we have to split the tree in such a way that it is divisible by the subtrees are also divisible by k. Now we will try to build our solution, and we will be building our solution on this example. In this example, we are given these values. These are the given values, where first one is n. N is the number of nodes in the given tree. Number of nodes are n, and the values are from 0 to n minus 1. So 0, 1, 2, 3 and 5, 6. These are the values. Okay, that's fine. And these are the edges from ith node to jth node, or you can say u to v. These are the edges, these are the node, and these are the values of the nodes from index 0 to n minus 1. So 0, 1, 2, 3, 4, 5, 6. These are the values given to us, and this is k. K is, we have to find the k divisible components. First thing is that the whole tree is also a valid component. So this tree, all the values sum of all the values is definitely divisible by k. K is 3 here, so definitely divisible by 3. Okay, that is one thing. And now what we have to do is, I need to split the tree in such a way that all the subcomponents are divisible by k. So let's say I am starting with 0 node, and now I try to go in the left direction, and I have to decide whether I can split over this edge or not. I will only be able to split over this edge if this subtree is giving me sum that is divisible by 3 equal to 0. And as you require the sum, you cannot go do it from the top to bottom. You have to do it from bottom to top. When you are coming here like this, when you are coming here, you are processing the whole subtree. Only after that you will be able to know what is the sum. So what I am saying is that, let's say we are going in this direction from 0 to here in this direction. I have to decide whether on this edge I am able to split the subtree or not. I have to split the subtree or not. I will be splitting if the sum of the subtree is divisible by k. I am coming in this direction and then processing 2, processing 3 and then processing 5, and then when I am returning back, I will be having sum of all the values. At node 2 we have 6, and node 6 we have 1, and node 5 we have 2. These values are coming from values array, and 6 plus 3, which is 9. So this is returning 9. This 2 will return. If 2 somehow is able to say that okay, 0 sum of the subtree starting with me is equal to 9, then 0 will be able to decide whether 0 have to cut this edge or not, because 0 have the right to cut it. If it is divisible by k, then 0 can do one thing. 0 will directly cut this edge. and sum from the left side, it can consider sum which was 9 divisible by k. Divisible by k is 0. So instead of capturing the sum, if it capture sum divisible, sum modulus k, so 0 can say that okay, from my left side I am getting some modulus k which was 0. Okay, if it is 0, I will just increment my answer. Answer is number of components we can make. Answer plus plus specifies that we are able to discard this edge. Okay, and when we are deciding, when we are going into the recursion, not at that time, when we are returning back from the recursion, at that time we are deciding, because when we are returning back from 2 to 0, we are deciding that the sum is equal to 9 and it is divisible by k. Modulus with k is 0, so just increment the counter and make sum equal to the modulus of modulus with k. So 0 will say that from the left side I am getting sum 0, and now from right side it will decide the same way. When it is going, let me clear this stuff. Here 0 will go on the right side. It is coming to 1, coming to 4, and then there is no node to process, and then coming to 3, and then when it is returning back, it will decide whether it has to process this subtree as an individual subtree or not, and whether we have to discard or cut this edge, yes or no. Depend on the sum. Sum at the value 1 is 0. Sum at fourth node is 5, and sum at third node is 1. So 5 plus 1, which is 6. So sum is 6. 6 is also divisible by 3. So we are able to make a cut here. Okay. So what I will do is, I don't have to make a cut actually in the tree. I just increment my answer again. I will increment my answer and make the sum updated with sum is equal to sum modulus 3, which is 0. So from left side also it is getting some 0. From right side also it is getting some 0. And this way we can move ahead. Okay. Now you might wonder why I have started from 0. It's totally up to you. You are free to choose any node to start with. Here I just started like this. Even if we start with 2, we'll be able to get the answer. Just that we have to make a DFS call, and when we are returning from the DFS, we will see if at any moment sum is becoming divisible by k. In that moment we'll just update the sum equal to sum modulus k, and if sum is divisible, just cut that component. Even if we look on the okay, now let's do one thing. Let's start from a different node. If I start from a different node, let's say I'm starting with 2. If I start with 2, I can go in 3 directions. Okay. One is, let's say I'm going in this direction. I'm going in this direction. I'm going, keep on going. Here the value is 6 and there is no further call, and it is returning the sum. Sum at the 6th node is 1 from the values array. So it is returning 1. Here the sum of this subtree is 1, and 1 is not divisible by k. So we don't have to cut this edge or increment the counter. Okay, we are not going to do anything. We'll just process our next subtree. And next one is from 2 is going to 5. Going the direction of 5, it is going till 5. At 5 there is no further edge. When it is returning back, the 5 will say, when it is returning back, it is getting some value. That is my return type of the solution or helper DFS function. Okay, you will understand later in a very well way. Okay, so when it is returning from the node at label 5, we have value 2 equal to 2. Okay, this is returning 2. 2 is also not divisible by k. So this subtree is also not valid. So we are not going to detach this subtree. Okay, fine. Now we have one possibility left at 2, one edge, or you can say one neighbor. That last neighbor is 0. Okay, we have come to 0, and from 0 I will further make a DFS call to its neighbor. From 0 they have two neighbors, 1 and 2, but 1 I will not go. I will not go to 2, sorry, I will not go to 2 because from 2 we are coming. We won't go to the 2 again, otherwise we will be stuck in the infinite looping. So we have to keep track of the node from where we are coming. From 2 we are already coming, so there is only one valid neighbor to go to. So that is 1. Okay, at 1, how many neighbor we can go? We can go to 2 more neighbors, which is 4 and 3. Let's say we are going to 4 first. We are going to 4, and when we are returning, okay, now we are returning, whenever we return, we have to check whether it is a valid tree to discard or subtree to cut off. At 4, at index 4, what is the value? Value is 5. Now it is returning value 5. I'm coming back to 1 again. It is checking that this value is 5. Okay, if this value is 5, no need to cut, no need to detach this subtree. It means this edge from 1 to 4 will remain intact. Now it is coming to the node 3. When it is coming to node 3, and while returning, it will see what is the sum this subtree is returning. Subtree with value only 3 is returning. At 3 we have value 1. It is returning sum 1. At 1 we went to the 2 direction. 1 at the neighbor 4, 1 at the neighbor 3. Both the neighboring subtree are not able to give me sum which is divisible by k. It means we cannot make a cut here. Now we will try to go further. When we try to go further, we will add one's value also into this. When we are going from 1, we will also add 1 value into this. So from left side we received 5. From right side we received 1, and presently at 1 we have 0. So in total it has become 6. So when the 1 is returning some value, it is returning 6. So at 0, it got to know that my this subtree, this subtree is returning a sum equal to 6, and 6 is divisible by 3. It means I can make a cut here. I am free to make a cut here. Okay, and if I am making a cut, I will also update the sum divisible by 3, because there is no sense of keeping 6, because 6 is also divisible by modulus, like 6 modulus k is 0. So there is no need to keep 6 into our sum, right? What I'm trying to say is that, let's say my value is 9 and 9 divisible by k is 0. Then there is no need to capture this, and it is something like this: 3 plus 9 divisible by k. Then discard this section completely. Okay, updating value of sum from 6 to 6 modulus 3, which is 0. So from 0 the sum is 0. Okay, and then the sum is 0 ultimately. Now when it is returning back, it initiated from 2 and it is returning back to 2 with sum 0. Okay, why 0? Because we have make a cut and we have taken a modulus. When it is coming to 2, the sum is 0, and 0 is also divisible by k. If 0 is also divisible by k, I can make a cut on this edge as well, and I will increment my counter. I am incrementing my counter 2 times when I am starting with 2. Okay, so this is the main concept of this problem. DFS, depth first search. When we are going till the depth, and when we are returning, we are deciding on the basis of sum whether we have to discard this subtree. Yeah, right, because when we are going from 0 to some other direction, we cannot say that whether we have to discard it. But when we are returning, then we are sure whether this subtree can be discarded or not. Okay, so this much we have to do, and these are the values given to us: n, number of nodes; edges, number of edges. We have nodes, we have number of edges. It means we have the tree. Okay, and from this tree you can start from any node. That is fine. And this is the value of 0th node, value of ith node. We can pick from this array, and this is 3. 3 is used to decide whether that subtree, let's say this is my tree and this is my tree, and at this node, yeah, this node, I have to decide whether I have to discard this subtree or not. I will discard on the basis of its sum. If sum is divisible by k, discard it, otherwise do not discard it. That's all we have to do. This is just DFS. And what we are doing here is we are visiting every node. Every node we are visiting. So in general, the time complexity of this approach will be going till order of n. So now we have to solve this question, and what we should do is, first of all, we will be initiating DFS from any node, and before moving to any node we are given edges and number of nodes. From these two values we need to firstly prepare the adjacency list. So our first aim is to prepare adjacency list. Once the adjacency is prepared, we have to make a DFS. We can make the DFS from any edge. So let's say we are making it from 0. It's totally up to you, whatever you can use. And yeah, the directions are not there. These are undirectional. So it's a normal tree. In the tree we usually have going to the left tree, going to the right tree, right? Going to the left child, going to the right child. Those directions are not there. It's undirectional. You can consider it as a graph. Graph with exactly n-1 edges without any loop, and it's a valid graph. It's also given in the constraints. Okay, prepare adjacency DFS from this, and while doing the DFS I will see if from any subtree I am returning sum which is divisible by k, then I will just cut that subtree. So I have to keep track of the sum from every neighbor. Okay, this much we have to do. So now, as this is the approach, what is the time and space complexity for this approach? What is time and what is space? What is time? First of all, we are preparing adjacency. We have n nodes and edges. Edges are n-1. So ultimately it will be going order of n. And we are preparing adjacency and visiting every single node. Okay, and what about the space? As we are preparing adjacency, we would be requiring some data structure to store the list. So time and space complexity is in the order of n and order of n. So we have n, adjacency we have prepared, we have values, we have k. Now we can start our DFS. From which node we are starting our DFS? Starting our DSR from 0th index. So let's say solution is the DFS call. We are starting from 0, and yeah, when we are making DFS call, we are visiting every neighbor, and before visiting every neighbor we have to make sure that that neighbor is not previously visited. It means we are not going to the direction from which we are coming. For that we can handle using a previous variable, previous node. What is the previous node? So this will be my current node, and let's say previous node is going to be -1, and along with this I also need to pass adjacency, and along with adjacency I need to pass values, and I will be passing k. And what about the answer? Let's say I am taking a global variable count. Count is initialized with 0, and I will be incrementing count whenever my sum is divisible by k. This is my solution function call. So in my main function, my first step is prepare adjacency. Done. And second one is make the solution call. And the third one is return count. Yeah, this is my main function. And now you have to just implement this DFS function call. And from this DFS function call, how we will implement? Firstly, we need to have some kind of variable. Let's say sum is this. Sum is initialized with 0. Now I will go to all the neighbors. For all neighbors, if current equal to previous, if current equal to previous, or current equal to parent node, in that case just continue. Do not do anything. We have to visit all the neighbors, and from every neighbor just calculate the sum. Sum plus equal to solution function. What is the neighbor? We have edge from u to v, and multiple v can be there. V, and the current is always current. This is destination edge, or you can say neighbor, and all the variables are same. So this is the sum. And now once I'm coming out of this loop, I will be capturing sum from all the neighbors. Let's say this is the tree, 1, 2, 3. And I need to see whether this edge I have to discard or not. Because if I discard this edge, I will be discarding the subtree. We are concerned about the subtree. So ultimately, my sum, I will be adding the current element as well. So I have processed this neighbor, I have processed this neighbor, and then I will be processing current node. Current node is current node. The value of the current node. Now you have captured. Now at this moment, you have captured the sum of subtree. And that sum of subtree can be divisible by k or not. So firstly, update the sum. Sum equal to sum modulus k. Okay, now this sum will be having remainder. What is remainder? So if this sum is equal to 0, then the count plus, otherwise do nothing, just return sum, so that next further calls will be processed. So this much we have to do. This is our algorithm, that for every solution function, count sum of all the neighbors, and then if sum of all the neighbors and the current node, this is the current subtree, is divisible by k, then increment the counter. Now let's write the code. From the code, you see how I'm writing the code, you will get more understanding. First of all, I have to prepare the adjacency list, and we are given n nodes. Nodes are from 0 to n minus 1. So if those are from 0 to n minus 1, I can take an array. And for array, every index will represent the neighbors of those nodes. So it's a array of array list. And now I have to fill the edges into the adjacency. Before filling the edges, I need to initialize this array as well. For I equal to 0, I less than n, I plus plus, adjacency of I. Now for every edge in edges, every edge is having u and v, int u, int v. U is equal to edge 0 and v is equal to edge 1. As it is an undirected graph, so we will be having v as a neighbor of u and u as a neighbor of b. So adjacency of u dot add v, and vice versa. It will be adding u inside v. Now the adjacency is prepared. I need to make call to my solution function, and in the end I can just return the counter. And count, I also need to access it in my solution function, so I will be taking it as a global one, int count, and this count is 0 in the starting, and in the end I am going to return it. What my solution function is going to have, let me start the DFS from 0, from node 0, and the parent of node 0 or previous to node 0 is -1. Okay, and along with this I need to pass adjacency. I also need to pass values and k. Now I have every single thing in my solution call. I will be implementing my solution function. It is returning integer variable, and solution int current node, int previous node, array list of integer array. This is my adjacency, and integer array values and integer value k. Okay, now I am at current node, and on that current node I need to visit all the neighbors. To visit all the neighbors, first of all I need to, let's say v is the neighbor, adjacency of current is, this is going to have all the neighbors, adjacency of current. Before that I'll need to take a variable sum as well, and after getting sum of all the neighbors, let's say I am at a node and I'm capturing sum of all the subtrees, and including that current node, that current node you can consider it as a root. Let me show you in the example. Let's say from 2 you are calculating the sum, and then you are calculating sum of left side, right side, and every other side. Let's say we are coming from this direction, so we will not be visiting that again. So at 2, what are the sum from all the neighbors, and then including the current value, that is going to be the sum of subtree starting at 2. So one condition I need to add is if my neighbor is equal to previous one. In that case, just continue, don't do anything. And otherwise do one thing, make a solution call and capture my sum. And after you have captured the sum, you have to add the current value as well. Sum plus equal to values current. This current is just the index, just the label of the node. The actual value is in the values array. Okay. Now we have to take the modulus of this sum. Sum equal to sum modulus with k. Instead of capturing the exact sum, just capture the modulus, just remainder, because we are only bothered about remainder. Okay. Now after this operation, if let's say my sum is the remainder, if it is equal to 0, it means that the subtree starting with current as a root is having total sum divisible by k. That means we can cut this edge. If we can cut this edge, I will be incrementing my counter. Count plus plus, and if count is not incremented, anyway return the sum. Okay, now this solution function call we have to make. Now current has become v and previous is my current, adjacency is same, values is same, k is same. Okay, yeah, this much we have to do. Let's run over sample test cases. Sample test cases are passed. I'm submitting the problem. It got submitted successfully and beats 100% of the Java solution. Okay, I hope you have understood the approach. If you have any doubt, you can comment down below. I will try to address your queries. Okay, thank you guys. Thanks for watching. Bye bye.